Hello everyone. Hi. My name's Peter Angren, and I'll be tackling the assignment for Group 1, which is under clipping a Bezier curve on a screen rectangle. So, as we start, gonna define the algorithm that we're gonna use for clipping, which we'll be using is the Castle-Jones algorithm, which creates an interpolate between consecutive control points to get an intermediate point, and iterates from that by using those control points to create secondary points, and then to go through other iterations to create a single point for plotting the curve. As we start, I'm gonna explain the code base as we go and run, and I'll show the final result. Let's start. So this is the final result for the Castle-Jones algorithm. It shows the original curve, clipped segment, and the clipping rectangle, which I'm going to explain all the parameters later as we do. As we start, sorry, I didn't define the group members. So it's group 1. Yeah, it's Peter Angren and Brian Kwena. I'll be handling the question 3 part, where I'm recording a YouTube video and submitting the assignment for the specified question, which was the Castle-Jones algorithm. As we start, I'm going to explain the first 2 lines of code, which are importing the Python libraries. The Python libraries that we use here are pyplot, numpy, and skyfi. The third library eludes me. I think I imported it down here. So yeah, scipy, that we imported scipy, installed numpy and matplot libraries for all of this to work. You're mainly gonna use the matplot library to use this. So the first part of the code, which is here, the function, the lab function, this part. The lab function is the linear interpolation function, and this function's purpose is to compute a point between 2 values p0 and p1 at a given parameter t, and that parameter t ranges from 0 to 1. So the use of this code is the cooperation. This code will be used as a cooperation for the Castle-Jones algorithm as we move on forward to the next block of the code. So as you can see, the Castle-Jones algorithm is L, which is the plot point t, which equals to 1 minus t multiplied by 0.0 plus t multiplied by 0.1. As we move on to the Castle-Jones portion of the code, the function where the points of the Bézier curve using the Castle-Jones algorithm. So we define under this function, we define the points, and we also calculate the points on the cubic Bézier curve control points. Here I'll be using a cubic Bézier curve. So yeah, so this function works in the following ways. First, it interpolates between consecutive control points, which is p1 to p0 to p3, to get intermediate points, which have been defined here, q0 to q2. The points are further interpolated to get secondary level points, which are R0 and R1. And then those points are also used to create the point B, where the curve will go through. It's a point on the curve and will be used to plot the curve. So the output of this function will be B, which is a single point where the curve will pass through the cubic shape. So the next part of the code is the clipping part. It clips the line segment against a rectangular boundary, and it works by checking the endpoints of the line segments if they are inside the rectangle using the is inside definition function. Yeah, this function. So it checks if the line segment is within the rectangle and defines it. And if both are inside, the segment is retained, otherwise it is discarded here. The only limitation for this function is that it only retains full inside segments. It doesn't handle partial intersections. That is where the endpoint is inside and the other is outside within the bounding box, the rectangle. So the next function of the code from line 27 is the function to clip the Bezier curve, which is this one. This is the function to clip the Bezier curve. So the purpose of this function is to, let me scroll up, is to clip a Bezier curve against a rectangular boundary. How it works is that it works in three ways. First, it is approximation. The curve is divided into linear segments over here. It's defined here. So the curve is broken down, is divided into linear segments by invalidating points on the curve for the values t. And the values for t is 0 and 1 in steps of 0.01, which gives us 100 segments. And then the next point is each segment is then checked by the clip line function here. So each segment is checked using the clip line function, and the segments that are entirely inside the rectangle are retained. And then the return value is here. So for this area, these initializes. It goes through a conditional statement, then initializes a loop to plot all the other points between the 100 segments. When the first segment is done, it loops, it jumps from that segment to the other one until all the segments are plotted. All the points within the segments are plotted within the bounding box, within the clip. So after they have been defined and the points in the segments have been defined, move on to the plotting. So yeah, plotting is over here, is down here. So I'll come to explain these points of the code later after I've done the plotting. So under the plotting, the purpose is to generate plots of the original Bezier curve in red. Yeah. So here, this function of the code, it plots the original Bezier curve in red. And it uses the algorithm, the Calcegels algorithm, to compute x and y coordinates for the curve. So here the values for that range, and so the Bezier curve is defined here. This is the x value and the y value, and those values are used to plot a point within for that the curve goes through and used to create the curve, and they are instantialized by the color red to be seen and labeled as the original curve. So, and for the clipped segments is over here. The clipped segments are enumerated here. It's almost in the it almost uses the same function as that plus the Bézier curve, but this one actually actually marks the segments of the curve that are within the screen rectangle, have been bounded, yeah, and they're given a blue color to show them the clipped segments. So the purpose of this part of the code is to plot the clipped portions of the curve in blue, and it loops through the clip line segments and plots each one individually into blue. Yeah, and after that portion of the code is the line for the rectangle. This line defines where the rectangle, the bounding box, or the clip rectangle, the screen rectangle, is in black, and it gives the color black. Yeah, it's been initialized here as black in color. So this function is the code for showing the clip rectangle, and then the last, this configures the plot. It configures the plot limit for the whole. It uses the library to configure the plot limits for the graph, and shows the legends and everything within the graph. This part of the code, it defines the port, the starting and the control points for the Bézier curve that will be used to create the curve, and these are the points that are defined for the clipping rectangle here, and they have been labeled well. I've used the comments to label them well, so even if you're lost, you can understand what the part of the code is. After that explanation, I can run the code to see how it works. Let's see. Oh, sorry, there's an error. Line 1, character 18. We try and run the code again. Yes, I actually typed the sentence I was explaining, single character I was explaining. So as you can see, this is the rectangle where the clipped point at the curve is the rectangle, and the blue part is the clipped part of the curve, and the red part is the original curve. So the blue part is within the clip range, and the red part is outside the clip range. So this code will give this result. Thank you for listening. This